Welcome everyone to the Richard Karp lecture in the sublinear algorithms program. Welcome first of all to the Simons Institute. My name is Sampath Kannan, and I can say as of the last week that I'm now the associate director at the Simons Institute. So let me just introduce the Simons Institute to the few people here, maybe one person here who doesn't know what it is and how it came to be. The Simons Institute was created by a generous grant from the Simons Foundation back in 2012, and they have been our principal supporters all through up to this point. Of course, Simons Institute, as you all know, is the premier venue for interaction in theoretical computer science, but also looking at other disciplines through the lens of theoretical computer science. And we bring together top researchers in the field in different programs. Now, the Karp lectures are to honor another very well-known figure who needs no introduction, Richard M. Karp, who was at Berkeley for a very long time. It's particularly appropriate to have a Karp lecture in the area of sublinear algorithms, because you could say that the Karp-Rabin algorithm for fingerprinting could be called one of the first, streaming sublinear algorithms there is before the fields existed. So it's great to be celebrating him in this program. The Karp lectures are made possible by donations from various people in the Simons community at large. So we encourage you to keep donating to the Karp Fund to support the Karp lectures. Today's speaker needs almost no introduction. Maybe a little more than Dick Karp, but maybe not much more. Rocco Servedio is a professor of computer science at Columbia University. He has done some seminal work both in the area of learning and property testing and sublinear algorithms, and in particular, the relationship between learning and testing. He has been chair of almost everything you can think of. He's been chair of all the major theoretical computer science conferences, as well as his department at Columbia and various committees that I'm aware of, I think. So without further ado, Rocco will tell us about property testing, new directions.
Thank you. Great, thank you very much, Sampath, for the kind introduction. It's a real honor to be here and to be delivering the Karp lecture. So thank you again to all the organizers. So let's get into it. I'm going to be talking about new directions in property testing. Perhaps, let's see if I can get the clicker to work. Working? Well, the laser pointer's working. I can use the space bar. Good. So I'm going to be talking about new directions in Boolean function property testing. There probably should have been a Boolean function inserted into the title of the talk. I'll give you a quick outline of what I'm going to be talking about. I don't know how many of you were here for Eric Weingarten's outstanding bootcamp lecture on Boolean function property testing, but this talk is going to kind of pick up where Eric's talk left off. So here's the structure of the talk. I'll start off by giving you some basic background on Boolean function property testing, telling you about the essentials of, what the problems are in this area, how the model works, and I'll, in particular, tell you a bit about these two kind of touchstone problems of monotonicity testing and junta testing, which have been kind of at the heart of a lot of the field. I'll move on to tell you about kind of my favorite property testing problem, which is a problem which I think belongs in this pantheon with monotonicity and juntas, but we understand it much less well. It's this problem of convexity testing. So we'll spend some time on that. Then I'm going to tell you for the latter part of the talk about kind of three extended frameworks for property testing. The first one of these is going to be an extension to make the problem a little bit harder, so-called tolerant testing or distance estimation. I'll tell you about a very new framework, relative error property testing, where I think there are a lot of exciting questions to explore. And I'll close with kind of a patchwork of a range of different passive testing frameworks, where in some sense, the testing algorithm has to succeed with one hand tied behind its back. And there will be a focus throughout on recent results and open questions. And I'd like this to be as informal as possible. So if there are questions at any point, please chime in and interrupt. OK, so let's get into it. I'll start off by talking about some basic background to make sure we're all on the same page. Good. So what's the basic setup of property testing? Well, it goes back to early work about 30 years ago. This is the seminal paper of Blum, Luby, and Rubenfeld. The very high-level idea of property testing, kind of in a bumper sticker level description, is that there's some unknown massive object. We might think of this object as a gigantic graph, like the internet graph. It might be a probability distribution over some huge domain. For us, it's going to be a Boolean function, which is like an exponentially sized object, as we'll see. And we're interested in figuring out whether this object has a particular property we're interested in, but we want to be sublinear. We're only going to inspect a tiny, tiny fraction of the object, much, much less than 1% of 1% of 1% of the object, okay? So kind of the silly cartoon here is that maybe you get a couple of bone fragments, something like that, tiny, tiny part of this massive object, some prehistoric animal, and you want to figure out, is it a dinosaur? Is it something other than a dinosaur, like a saber-toothed tiger, something like that? So whenever we want to solve a problem like this, if we're only going to be looking at a tiny fraction of the input, of course, we have to sort of, bound our expectations. The algorithms we use should be randomized algorithms. We shouldn't always look at the same tiny fraction, the prefix of the input or something, or else we could easily be misled. And we're going to have to settle for approximate guarantees in terms of what we get out of the algorithms. So refining the notion a little bit, we'll be interested in kind of distinguishing between these two cases. Does the massive object, which we just probe in a couple of places, inspect sort of locally, does it have some property that we're interested in? Or is it kind of very far from having that property? This is a problem we could hope to solve in the sublinear regime, okay? So like I said, the massive objects we'll be thinking about will be Boolean functions. If you're familiar with Boolean functions, they need no introduction. They're just functions that map n-bit strings to single binary outputs. And if you're not familiar with them, just think of them as binary classification rules. It's a rule which someone gives you an image and it says yes if the image contains an elephant and no if the image doesn't contain an elephant. Kind of functions with yes, no outputs, binary outputs. And we should think of such functions as truly massive objects. If the domain is the set of all n-bit strings, there are of course 2 to the n output bits. The truth table, the description of such an object is of size 2 to the n. Okay, so it fits into our framework of massive objects. Good. So how does this property testing thing work? We get to access the object, like I said, by making kind of local probes. We think of ourselves as having oracle access to an oracle for this function. So we can think of the function, kind of this cartoon over here. This is the way I'm going to be drawing the Boolean hypercube throughout the talk. We think of the function as just a subset of the domain, the subset of the inputs where the function outputs 1. And how's it going to work? Well, the algorithm's over here on the left. It makes a query. It says, hey, I'd like to know whether or not this particular point is in the function or not, and it gets an answer. In this case, the answer would be 0 because it's in the 0 region of the function, right? The algorithm makes some more queries, sees how these different points are labeled that it's interested in. Finally, it makes its last query, and then it has to come up with its decision. Hey, I think this object has the property versus, hey, this object looks like it's far from having the property that I'm interested in. And we'll see a lot of examples of this and make it more concrete as we go. So I want to right away call out a distinction between 2 basic flavors of property testing algorithms, because it's going to be important for a lot of the things I'll talk about. We can think about either adaptive or non-adaptive testing algorithms. Let me start with the simpler algorithms, the non-adaptive algorithms. Intuitively, non-adaptive algorithms are ones where you have to decide on all the queries you're going to make up front. It's sort of like you're loading your experimental equipment into a spaceship, something like that. You're not going to be able to sort of decide to do a different experiment once you get the results of the first experiment back. So the picture is something like this. You choose all of your query strings, feed them all into the oracle for the function at once, get back all the answers in one fell swoop, and then you have to make your decision as to whether or not the function had the property. Okay, this is a little bit more restrictive than kind of the adaptive algorithms that I illustrated on the previous slide. In adaptive algorithms, you can see the answer to your first question. Oh, I see this point was a 0 input for the function. Oh, this point was a 1 input for the function. You get to choose your later points based on the responses that you get to the earlier questions which you're making. Okay? So it should be clear that adaptive algorithms are, finishing out the picture, it should be clear adaptive algorithms are more powerful, right? You get to have this kind of intelligent, informed choice of the later queries you're going to make. It should also not be surprising that adaptive algorithms are probably going to be harder to analyze. And we'll see that throughout the talk. The state of our knowledge, our understanding of adaptive property testing is not quite at the same level as our understanding for non-adaptive versions of the problem. Okay, good, so far so good. So I've been talking about, hey, does my function have the property or is it far from having the property? Well, what do I mean by far? We need some well-defined distance notion. I've tried to illustrate that on the left-hand side of the slide. So kind of the red region, think of that as like defining a function f. The yellow region defining a different function g. We'll talk about the distance between functions f and g, at least in this part of the talk, as being just the symmetric difference, the fraction of the domain, which is either yellow but not red or red but not yellow, divided by the total number of all points. So it's like the distance between these two functions under the uniform distribution over all inputs. Okay? And if we want to talk about the distance from a property the distance of a function f to an entire property, like how far is f from having this property? Well, that's just the minimum distance between f and any function g that has the property. We can always think of a property as just the collection of all functions that have that property. Okay, so it wouldn't be a talk on property testing without what I think of as Clément's famous egg diagram. This is kind of a good way to sort of visualize property testing from a bird's eye view. This is a cartoon of all Boolean functions, so every possible Boolean function, that's what this outer ellipse is, okay? The set of functions that have the properties, the green circle in here, and the idea is that you don't know what function you've got. It might be in here, it might be in the gray region, it might be in the red region. If it's in the green region, after you've made your queries, you should accept. You should say, yes, this function has the property, because indeed, these are the functions that have the property. If it's in the red region, meaning that it's far from every function that has the property, then you should be rejecting those functions. And we have this kind of gray zone of indifference. The idea is that, you know, any function which is epsilon close, it's close to having the property, but it's a little bit different from any function that has the property. We can't be expected to maybe give a correct answer on functions like that, right? They're right at the boundary. There's no way we could tell whether it actually has the property or doesn't quite have the property. So we're interested in distinguishing the green guys from the red guys. And where we don't have any a priori knowledge about what the function is, it could be any function. So we can see there's this distance parameter. Throughout the talk, I'll just take it to be a fixed constant. Think of it as 0.01 for simplicity. So far, so good? Okay, I don't see anybody crying, so let's continue. Good. So just kind of a quick statement about what we'll be shooting for, like a benchmark of sort of a good property testing result. Like I said, we can think of a property as corresponding to just the class of all functions that have the property. And it's not too difficult to show, it's a well-known result from the 90s, that if you have a learning algorithm for the class, for a particular function class for this property P, which can learn the class, any function in the class with Q queries, then we'll also have a testing algorithm which can succeed with Q queries. It's a simple transformation. You just basically run your learning algorithm, you have some hypothesis, and you check, oh, did this hypothesis, does it sync up? Is it correct on random points that I draw? So if you can learn, you can test with the same efficiency, but what we'll be interested in doing is testing more efficiently than we can learn. Learning feels like overkill. You're computing some big, complicated hypothesis. For testing, you're supposed to output a single bit. Does it have the property or does it not? So we should hope to do that more efficiently than we can learn. And that's going to be the central goal we're interested in for different classes. Can I do this more efficiently than I can learn? Can I test more efficiently? Okay, so I think I can tell you now about a couple of kind of classic property testing problems. The first one is going to be testing whether a Boolean function is monotone or not. So this is probably a notion familiar to many of us. A monotone Boolean function is basically one where flipping input bits from 0 to 1 can only ever flip the output bit from 0 to 1. It sort of is monotone increasing in each of the coordinates. Okay, a cartoon would be something like this. If I walk up the Boolean hypercube from the all zeros input by flipping bits from 0 to 1, eventually I go into the 1 region and I stay in the 1 region. I could never be walking up, flipping bits from 0 to 1, and have the function's value go the other way from 1 to 0. This would be an example of a far from monotone function because I'd have to change this function on many inputs to give it the structure of a monotone function where it has this property. Okay. So for monotonicity testing, you have a completely arbitrary unknown function. You don't know if it's monotone, you don't know if it's far from monotone. You're going to make some queries and try to figure out, is it in the blue region or is it in the green region? Well, we just saw from the last slide, we could do this by running a learning algorithm for monotone functions, a uniform distribution learning algorithm. Unfortunately, the best known algorithms, and they're provably optimal, are highly inefficient. They run in time essentially 2 to the square root n number of queries. So this is a mildly exponential dependence on the dimension. We're not really happy with trying to test whether a function is monotone with such a large number of queries. We'd like to do better. Fortunately, we don't have to do any work because the community's done a lot of work for us over the years. This has been an intensively studied problem, and just kind of to cut to the chase, we have almost matching upper and lower bounds. So it's known that with n to the 1/2 many queries, this is a famous result of Coate, Minzer, and Safra, we can test whether our function is monotone or not, test whether it's monotone or far from monotone. And there's also an almost matching lower bound due to Chen, Weingarten, and Xie, n to the 1/3 queries. So instead of something exponential like 2 to the square root n to learn the function, this mild, small degree polynomial number of queries is necessary and sufficient for testing monotonicity. Okay, and I want to call your attention to kind of the picture down here. I'm going to refer to this throughout the talk as the shaggy Boolean function. Okay, it's kind of central in the proofs of these lower bounds. The proof of the lower bound relies very heavily on exploiting the structure of this kind of special, particular monotone Boolean function, which I want you to think of as kind of hairy or shaggy. It's a function which has the property that many inputs, a constant fraction of the inputs, are kind of robustly on the boundary of this function. Okay, so think of it as like something with all these hairs, and you're always like close to a hair or on a hair kind of thing. We'll see this repeatedly. Okay, so this is good news. This is an important property testing problem, and we basically understand how to solve it. We understand the query complexity up to a small factor. Another important property testing problem is junta testing. Let me tell you what this is. This is a problem which sort of is very relevant to the topic of identifying or understanding the number of relevant variables for a function. It was studied heavily in learning theory. So a k-junta is just a fancy way of saying you have an n variable Boolean function, but it has the property that only k of the n input variables actually matter. The other n minus k are irrelevant variables. And you should think of k as like 5 or 10 or log n or something very small in this context, okay? So this is an example of a 4 junta. Maybe we have a million different Boolean variables, x1 through x a million, but only these 4 variables, x71, x8, x22, x99 are the ones that the function depends upon, okay? So we could, again, ask this question, well, what can we get from learning? It's not too hard if you think about k-juntas for a little while to see that you can have a learning algorithm which makes a number of queries which is exponential in k. This should make sense. The truth table of a k variable function is of size 2 to the k, okay? And there's also dependence on log n. Basically, to figure out the name of a single variable, you would need log n bits of information, log n queries, okay? So we could test by running a learning algorithm if we were willing to be exponential in k and have a dependence on n. But it turns out this is also a very intensively studied problem in property testing. Basically, k queries, completely independent of the ambient dimension n, are both necessary and sufficient for testing juntas. So we have this exponential savings in terms of k. We don't have to do anything like learning the truth table, and we don't have to have any dependence on n at all. That means we'll never be finding a single variable in the junta, but somehow we can still figure out that it is a junta, which is our function. Okay, so this is a good point to pause for questions. Yeah, Carmen.
Well, are all these results for the uniform distribution or the distribution?
Great question. So far, everything I've said is going to be about the uniform distribution. We will change to somewhat different distributions later, but I bit my lip when I was making up this talk. I'm not going to really talk about distribution-free learning much. Yeah. Good. Any other questions? Okay, let's keep going then. So we've kind of seen the basic stuff about Boolean function property testing, and we saw that these problems of junta testing and monotonicity testing, they kind of live in the Boolean function property testing Hall of Fame. They've been very heavily studied over the years. So next I want to tell you about, probably my favorite property testing question. It's this convexity testing problem. I think it also belongs in the Hall of Fame, and that's part of why I'm going to tell you about it, to hopefully convince you that it's an interesting problem and maybe even get you to think about working on it. So, okay, what's up with convexity testing? Again, we should think of the problem instance as being the same way a Boolean function, the input for regular Boolean function property testing is really just a subset of the domain. That's what a Boolean function is. We're going to think of the problem instance as an unknown subset of the domain, and we're just trying to test whether this subset is convex. Okay, so here's a drawing of a convex function. What does convex mean? It just means if you have 2 points like A and C, all the points on the line between them are also in the set, if A and C are in the set. Whereas a function is a set, I should say, is far from convex, or is non-convex if it's something like this. You have 2 points A and C that are in the set, but the point in the middle is not in the set. Okay, and more rigorously, if I had to change this set by a lot to make it into a convex set, that would mean that this set is far from convex. I'll talk more about the details of this distance notion and so on right now. So, yeah, what's the domain? This is actually a question we have to think about a little bit. And I think this is kind of the reason why convexity testing has not been in the pantheon of kind of these, foundational Boolean function property testing problems people think about. If you think about it for a minute, it doesn't make sense to think about convexity testing over our favorite domain of n-bit strings, because the Boolean hypercube, every vertex is an extremal point, right? It's like everything is in the convex hull. Every point is a point on the boundary. If you take any subset of the Boolean hypercube, that's consistent with some convex set. Any subset can be obtained by intersecting the hypercube, the discrete corner points of the hypercube with a convex set. So you can't really think about convexity testing if you're like, oh, my domain is the Boolean hypercube, which is often what we like to think about. But that's no problem. I think we should just switch domains. So people have actually studied convexity testing in the low dimensional setting for a number of years. You can have the domain be a discrete grid of two-dimensional points or the continuous, unit square, something like that. What I want to focus on is high dimensional convexity testing, in particular the picture on the right, where the domain is going to be just Euclidean n-dimensional space. Okay, so we're interested in high dimensional continuous convexity testing. And this is a much less well understood problem. Okay, so what's going on? The setting is we're interested in subsets of the domain Rn. The input, function or set is just an arbitrary subset of Rn. We need a distance measure, right? What do I mean that this set is far from this set? Well, there's a very natural distribution which is screaming out to be the one that you consider, which is just the standard Gaussian distribution over Rn. It's extremely natural. It has all these nice mathematical properties. I think there's a long case to be made, which I'll spare you, for why this is kind of the right analog of the Boolean function question. So we'll be thinking about the standard Gaussian distribution over Rn, and the distance between two sets now is exactly what you would expect it is. This is a little bit small, I apologize, but if you have one set K, which is like this circle, and another set L, which is, I guess, this octagon, you just look at the symmetric difference of those two sets, and you ask, what's the probability that a draw from the Gaussian distribution falls in that symmetric difference? It's exactly analogous to like the Boolean function case. You look at the symmetric difference as a fraction of the Boolean cube. You're now just looking at kind of the Gaussian volume of this symmetric difference. Okay. So this is a well-defined, formulation of the problem of convexity testing in high dimension. Again, it's mathematically very clean. It has close connections to Gaussian geometry, and maybe unexpectedly, or maybe not unexpectedly, if you went to Shivam's talk at 2 o'clock today, it turns out to have a lot of connections to the study of monotonicity. And I think these connections should be further exploited and further understood. So let me tell you a little bit about this analogy, which has emerged in recent years. It's an analogy between monotone Boolean functions, where we think about the uniform distribution as kind of the ambient distribution over inputs, and symmetric. They don't always have to be symmetric, but for now, think of it as symmetric convex sets in Euclidean space, where I have the Gaussian distribution as kind of the ambient distribution. So you might say, all right, what do these have to do with each other? They don't look like there's much connection here. Let me try to convince you in a superficial way. If you start anywhere in the Boolean cube and you're like, oh, I want to walk up to the all ones input, my hand is not that steady, but you see, you'll eventually go from the 0 region into the 1 region, you'll stay in the 1 region, okay? Similarly, if you kind of start out here in the Euclidean setting, you're like, oh, I want to walk in toward the origin, you'll start in the 0 region, you'll enter the 1 region, and since it's a symmetric convex set, you'll stay in the 1 region until you get to the origin, okay? That might look pretty superficial, like, okay, how much resemblance is there really between these two settings? There's much, much more to it. I'm not going to go through this slide, but over the last number of years, people have established connections between the analytic structure of monotone functions and the analytic structure of convex indicator functions of convex sets in the continuous setting, combinatorial things like density increment results, correlation inequalities. These structural results have implications for algorithms. In particular, the learning picture lines up both ways. Yeah, question?
Symmetric.
Oh, just symmetric around the origin. If x is in the set, not x is, minus x is in the set. Yeah, sorry, I should have said that. Yeah, actually, I was a bad boy. This is, I think, a pentagon, so it's not symmetric. But yeah, I shouldn't have said that. Anyway, yeah, so there's all these structural results, analytic results, structural results, combinatorial results, algorithmic results, where if you kind of know what happens in the monotone Boolean setting, you can write down the theorem for what will happen in the convex Gaussian setting. The proofs often don't look anything like each other, but the results really seem to transfer back and forth with kind of a surprising level of fidelity. Question, yeah?
So if I want to understand things like the query complexity for various tasks in this setting, is there like a notion of what kind of oracle access I have, what kind of query access?
Great question, yeah. So this convexity testing question we're thinking about, it's exactly, again, you just get to submit an input point, which now instead of a bit string is a vector in Rn, and you're just told it's in the set or it's not in the set. So it's the same kind of query access we had before. Yeah. Good question. Question, Sepper.
These analogs between them or the proofs are different. Is it just a coincidence that all of them keep happening? Or?
Yeah, I wish I knew. Again, in many cases, the proofs don't look anything like each other. There are some statements like these correlation inequalities. Harris-Kleitman is trivial. Gaussian correlation inequality took 40 years to prove, but they're really like the same statements, just in one setting versus the other statement. So I don't think there's like an easy dictionary that we're all missing. It's a little weird. Yeah, we should have a beer later and I can talk your ear off about this. It's
Like they don't imply anything for each other.
I don't know of implications like that for these kinds of things. Yeah. So anyway, if you believe in this analogy, and people in this room who have worked with me know I believe in this analogy, you would probably think, maybe convexity is testable because monotonicity is nicely testable, right? We know we can test monotonicity with something like root n, n to the 1/3 many queries. This is, one of our top results in this area. Sadly, convexity testing we do not understand well. The best convexity testing algorithms we have are based just on learning convex sets. In fact, they only use random samples. They don't even use queries in an intelligent way. And they're highly inefficient. They use 2 to the root n queries. This is the same way monotone functions, you need 2 to the root n examples to learn monotone functions. We saw a few slides back. So I believe that there's a much better result to be obtained here. We don't know how to do it yet, though. I think this is a nice research opportunity. Yeah, that's hard. Yeah. It's hard. Yeah, there's strong lower bounds for that. Yeah. Okay, so there has been some recent progress on lower bounds, not on algorithms, unfortunately, for convexity testing, but for lower bounds. I don't want to go through all the technical details of this polynomial number of queries, that polynomial number of queries. I just want to impress on you that these lower bounds, which we've obtained recently, are obtained really inspired by this analogy. You look at the shaggy monotone Boolean function, which was useful for monotonicity testing lower bounds, and you think about what would be a shaggy convex set, a convex set analog where a lot of the kind of, the boundary is like a very big kind of shaggy thing, right? And inspired by that, there's, the proofs don't look that similar, but the idea gets you in the right direction and gets you to a consistent statement. And similarly, some central limit theorem techniques, which are useful in the monotonicity setting, turn out to be useful in the convexity setting. I should say all these quantitative results are completely consistent with having just a parallel picture between monotonicity and convexity. So I think this strengthens my belief a little bit that, yeah, there really is a correspondence here, but we're just missing the positive results. We only have not very impressive testing algorithms for convexity, but the lower bounds are starting to catch up to the state-of-the-art lower bounds for monotonicity. Okay, Leon. No, it's more, that works for LTFs and PTFs, but I don't know of a meaningful correspondence there for convexity. Yeah, we could talk about that more later. Okay, so that's what I wanted to say about convexity testing. Okay, I'm doing okay on time. Let me switch gears now. That was like a concrete problem that I hope you all go off and work on and solve. I'm going to tell you now about different frameworks for property testing. So I'll start off by talking about so-called tolerant testing or distance estimation, and I'll use this silly picture of a guy with his thumb to keep this distance estimation notion in your mind. Okay, so this is a framework which makes property testing harder. Okay, it was introduced by Parnas, Rubenfeld and Ron about 20 years ago. Let's think of the usual property testing setting. What are we trying to do? We're trying to figure out whether the distance from our unknown function to the property is 0, i.e. it has the property, or whether it's at least epsilon, it's far from having the property. So standard property testing is kind of like distance estimation. You're just trying to estimate whether the distance is 0 or something big, at least epsilon. You can generalize this in a very natural way by saying, oh, okay, just in general, I have 2 parameters, epsilon1 less than epsilon2, and I want to do distance estimation. I want to figure out whether the distance from my function to the property is at most epsilon1, so it's somewhere in the bigger green region, or at least epsilon2. Okay, it's just a generalization of the standard setting. Standard setting is like you take epsilon1 to be 0. So you can imagine this certainly can't be any easier than the original property testing problem. In fact, it turns out to be quite a bit harder in 2 senses. It's harder, strictly it tends to be harder as an algorithmic problem because you don't have the same kind of structure. In the original case, hey, if it's a yes function, it has the property, right? You can exploit the fact that it has the property. Now you can no longer exploit that. It doesn't quite have the property, and so there's less to work with. Also, in terms of kind of our research progress, whoops. Well, that's it. Thank you. I think this came out. Let's see if it goes back in. Yeah, also in terms of kind of our understanding of research results here, it has historically been much harder to prove results about tolerant testing, both upper bounds and lower bounds. But there has been some considerable recent progress, and I'll tell you about some of that. In particular for Hunter testing, there's been some really nice results, some of them coming out of Berkeley, like this work of Avishai, Michael Whitmire, and Vishnu Iyer in recent years. Some of it coming out of Columbia, a number of these other results. People have thought about tolerant Hunter testing ever since the very early days of thinking about tolerant testing, and now we're really closing in on understanding it, it seems. So I'll highlight these 2 results, Shivam Nadampally and Shamal Patel, both of whom are here in the front row recently proved tight 2 to the square root k upper and lower bounds for non-adaptively testing whether your function is a k-junta in this tolerance setting. Okay, and very recently, Shyamala Patel and Shi Chen also proved a super polynomial lower bound for the adaptive version of the question. Okay, so for non-adaptive junta testing, we totally understand it. It's hard. It's not quite exponentially hard, 2 to the k hard. It doesn't depend on n, but it's kind of hard. For adaptive testing, well, it's still pretty hard, but there's an exponential gap here between 2 to the root k and just this barely super polynomial bound. So there's been a lot of progress, but there's more to understand for junta testing. There's also been progress recently on monotonicity testing. So I mentioned that we can learn monotone functions with 2 to the root n queries. We can actually learn them in kind of a strong noise robust sense, which gives us even tolerant monotonicity testing with 2 to the root n queries. And there were lower bounds which kind of hinted that something like this might be close to the truth, kind of these barely mildly exponential lower bounds in a demanding regime, in the regime where, oh, epsilon 1 and epsilon 2 are very, very close to each other. And I don't want to go into a lot of detail here, other than to say that kind of the essential idea of this lower bound was to kind of use the boundary of a particular monotone function, the majority function, to sort of hide the distance to monotonicity in those boundary inputs. Quite recently, there was an improvement to this result, so it's stronger in 2 ways. It's quantitatively stronger, and it works in the regime we're interested in, where epsilon 2 and epsilon 1 are far from each other. We have this wide band. The idea here was, again, to kind of use these shaggy monotone Boolean functions. They have a lot of boundary, right? There's kind of more room to hide what's going on. At a very high level, this was kind of the essence of some of this recent progress for tolerant monotonicity testing. So we saw there's been progress recently on tolerant junta testing, tolerant monotonicity testing. What about Rocco's favorite problem, convexity testing? Well, there was some interesting work on kind of a warm-up to this problem a number of years ago. This is Day, Mossel, and Niemann. If you think about a convex set, any convex set is just an intersection of half spaces. In general, you need infinitely many half spaces to be intersected to get an arbitrary convex set. What if I say my convex set has to be super simple? Like it's 1 half space, or it's an intersection of 4 half spaces, something like that. These guys were able to show that, if you want to test for the property of being an intersection of k half spaces, you can do that with a query complexity, which is basically a polynomial in k to the log k, something like this. And I'm highlighting this because it's a cool paper and it has really nice connections. They kind of look at each half space, the direction for each half space, as almost being like a variable in a junta. You should think of an intersection of k half spaces as something like a k junta in continuous space. Okay, so it's like another nice kind of illustration of this, this like discrete continuous connection. If you want to know how many half spaces you need to approximate a convex set, go to Shivam's talk tomorrow at 2:30. He's giving a talk about that topic tomorrow. 2 o'clock, 2:30? 2:30, 2:30, something like that. Yeah, so good question. I mean, certainly if we let k be infinity, that's convexity testing, right? You allow infinitely many half spaces. And there was recent progress here too. We have the upper bound, which again, just kind of comes from this analogy. The same way that we can learn monotone functions with 2 to the root n queries, we can learn convex sets with 2 to the root n queries. And we very recently got this 2 to the 4th root n query lower bound for testing convexity in this tolerance setting. And you're probably like, oh, I just saw 2 to the 4th root n for the monotonicity thing, and that's not a coincidence. The construction here, kind of the key thing in this convexity lower bound, is a convex analog of this sort of shaggy Boolean function, the way it was used for hiding the non-monotonicity. Now we're hiding the non-convexity using the shaggy convex set again. So again, it's this analogy kind of bearing fruit for us in terms of getting results on convexity from monotonicity. Okay. That's pretty much what I wanted to say about tolerant testing. Questions on that part? Good question. So here we're able to achieve this lower bound even for a constant gap, which is like a stronger result because the yes case and the no case are like far from each other, but it's still hard. Yeah, good question. Okay, good. Let me then, question, yeah.
For any of those results about tolerantly testing juntas, are there gaps between best query complexities and best runtimes?
Great question. I'll defer that to the tolerant junta testing experts in the audience, Shamal and Shiva. Maybe we can ask them about it later. I don't know the answer. I think there might be, but we should ask those guys. Yeah. Okay. Okay, good. Let me tell you now about this very, very kind of recent model that we've been thinking about, so-called relative error testing. And the silly icon here is going to be a housefly and a blue whale. Good, so what's the deal with this relative error testing setup? Well, the motivation here is that, sometimes you might be interested in a massive object, but it's not quite as massive as like a really massive object. Basically, the thinking is you should look at objects at a scale that is appropriate for those objects, right? You don't want to use the same measurement instrument to study a blue whale as you do a housefly, right? They're both big objects. A housefly, I learned in making up this talk, has about 5 million cells, but it's not the same scale as a blue whale kind of thing. So to be a little bit more quantitative, there are a lot of interesting Boolean functions where which actually only have a very small fraction of all inputs being satisfying assignments. Like think of a Boolean function with 2 to the n over 2 satisfying assignments. Well, the fraction of assignments that are yes inputs that are satisfying is 1 over 2 to the n over 2. So that's really tiny. But also 2 to the n over 2 is a large number of satisfying assignments, right? It still is a massive object. However, okay, I should throw a sop to motivation. Something like combinatorial drug discovery, I think, is an example of where something like this actually plays out in practice, right? You've got some combinatorial explosion in the number of possible candidate molecules, but whatever property, whatever characteristic you want your drug to have, probably only a tiny fraction of these candidate molecules actually have this property, right? So it's like a function with a very small fraction of yes inputs that could naturally arise in like some kind of real world scenario. However, if we're interested in kind of testing sparse Boolean functions which output 1 only on a very, very small, little o of 1 fraction of inputs, the usual model is not good for that because any sparse function is super close to the constant 0 function in our usual distance measure, right? So like, our standard distance measure is I look at the distance between two functions as just being the size of the symmetric difference divided by 2 to the n. But if f is a function with, I don't know, only 2 to the n over 2 satisfying assignments, I can just take g to be the 0 function, and it's super close to the 0 function. So things aren't interesting. It's like you're testing the 0 function. Okay? So we have to do something different. And I think something you can do is super simple. Just renormalize. Normalize, look at the distance between f and g as not being the fraction of all satisfying assignments, 2 to the n, but make it the fraction of satisfying assignments to the function f. You're sort of inspecting f or looking at distance to f on the scale of f itself. I think it's a more natural way to do things. I will change my query model, at the bottom of the slide. So I'm going to give myself both access to queries. I can still query the function, but I also kind of have to give myself access to random satisfying assignments. If I can't get random satisfying assignments, I may just never be able to find any yes inputs at all, right? It's this tiny little, island of yes inputs. I have no idea where they are. You wouldn't be able to find them. So we'll still allow ourselves to make black box queries as in the usual testing model, but I don't know if you can see it as I press the space bar, I'm getting these like random positive examples as well. Okay, so I have access to uniform satisfying assignments and I can make these black box queries. And now it's a reasonable kind of question to think about. Okay, so I think there's a whole space of questions here. People studied this relative error testing framework for images, for like two-dimensional functions on hypergrids previously. I don't think it's been studied before for high-dimensional functions, for like Boolean functions the way we often think about them, n input bits, 1 output bit. So I think there's a really nice question here. For your favorite property, what happens in terms of testing sparse functions in a framework like this? Does it get easier? Does it get harder? And the answer seems to be, we so far have kind of looked at 2 different particular properties, and it seems to be, well, not clear. Sometimes it gets easier, sometimes it gets harder. So I'll tell you in the next 2 slides about some relative error testing results for testing monotonicity and for testing this other property I haven't mentioned yet, the testing whether a function is a half space or not. Clement? Excellent question. So if you can learn from only satisfying assignments and you're also allowed queries, then you can also test in our model with the same query complexity. We'll want to beat that baseline. Yeah, that's a great question though. The answer is yes. Okay, so let me tell you first about relative error monotonicity testing. So the picture to have in mind now is like, the function is very sparse. It only has a small number of satisfying assignments. A priori, they might be anywhere in the Boolean cube. But you have like some sparse function. In particular, let's let capital S be the number of satisfying assignments that the function has. Okay, so it's S sparse. You don't need to know S for these results. Can we test it? Like how many queries do we need to test in this relative error sense? So we have a decent understanding of this. It kind of parallels our understanding of standard testing. We know that log S samples and queries turns out to be enough. And we have a lower bound of log S to the 2/3 samples and queries. So it's a little bit like the standard setting where we had a root n upper bound and a cube root n lower bound. Now we have a log S upper bound and a log S to the 2/3 lower bound. And I'm not going to go into much detail about why these things are true, but I'll just mention, since the complexity is basically log S, if S is small, this is sort of easier. It's easier. It could be a much smaller number of queries than n to the 1/2 or n to the 1/3 or whatever if you're testing a sparse function. Again, kind of the reason that the lower bound we're able to get 2/3 here instead of like 1/3 in the standard model is intuitively if your function is sparse, there might not be as much room to kind of have structure reflecting monotonicity or lack of monotonicity. Very, very hazy high-level intuition. But anyway, the takeaway from this slide is for monotonicity testing, if you're interested in testing a really sparse function, the problem gets easier. The number of queries which are necessary and sufficient goes down below the number of queries in the standard model, which we saw as like root n or cube root n or something like that. Okay, so monotonicity testing gets easier. However, for this other problem, well, let me tell you about this other problem, testing half spaces. I haven't talked about half spaces yet, but if you've seen anything with machine learning, you probably know what half spaces are. They're the backbone of machine learning setups. Testing half spaces, okay, the property we're interested in is just, is your function computed by a half space? A half space is just, a hyperplane cutting through the Boolean cube or Rn or whatever your domain is, and all the points on one side of it are yes inputs, one inputs, all the points on the other side, the function outputs 0, okay? So we're interested in testing whether the unknown function is a half space or is far from a half space. This has been studied in the standard model, and it turns out that in the standard model, constantly many queries are sufficient to test whether your function is a half space. You don't need any dependence on the dimension. Okay, and very, very hazily, the way this works is it kind of combines techniques from Junta testing with central limit theorems. You might say, why are central limit theorems in the picture? Well, look at your half space. If it's the uniform distribution, you think of x1, x2 through xn, they're like independent random variables. So half spaces are kind of all about central limit theorems, right? You have a sum of independent random variables here on the left. That's like a CLT kind of situation. So somehow the combination of juntas and CLT niceness means that in the standard model, in the usual model, not the sparse model, you can test half spaces with constantly many queries. So very recently, we were able to show that in the relative error model, we have this extremely impressive lower bound of log n, many queries. I'm joking when I say it's extremely impressive. This is an extremely small lower bound, right? Log n is not a very fast growing function, but it's kind of infinitely bigger than constant, right? Like there's a, don't laugh, Shibam. There's a dependence on the dimension now where there wasn't a dependence on the dimension in the standard setting. So for half spaces, we kind of provably understand that relative error testing becomes harder than it was in the standard model. And a little bit of intuition for why this is true is, the positive results relied on these central limit theorems. Central limit theorems don't work so well if you're interested in a relative error setting. I doubt you can see this, but the idea of a central limit theorem is you've got this like, smooth curve, which you probably can't see. And the discrete sort of sum of independent random variables is going to be, faithfully close to that smooth curve, the smooth CDF of the function. These things are true in terms of absolute error. They're not true in terms of relative error. If you went in with a magnifying glass and you looked at what's happening, very, very far out in the tail, the smooth curve might be 1,000,000 times higher than the discrete curve or vice versa. So you lose kind of the central limit theorem tool, and indeed, it turns out there's actually a lower bound. It's not just that the tester fails, like it's not true. Question?
So what's the analog for the Shaggy function in the half space setting? Is it the same?
Great question. The Shaggy function kind of is not a half space. The function with the biggest boundary that is a half space would be just the majority function. But the Shaggy function was like a monotone function. Half spaces are a little too structured. They can't be Shaggy in this way. Yeah. Question, yeah.
Previous slide, it seems like the notion of cost is samples plus queries.
Yeah, samples plus queries.
Is there any, like, if you have a little bit more samples, like if samples are in a way
Cheaper. Yeah.
Would you get better?
I see. You're asking about trading off, like, oh, maybe I spend a few more samples, but I don't have to spend as many queries. That's a good question. We haven't thought about that kind of thing yet. There are related settings. If you want to do this, we have some positive results, which I'm not telling you about, for half space testing in the Gaussian setting. where we have sample-only algorithms, but they don't use any queries. And they make, I think, square root n. They use like square root n samples or something like that. So yeah, there might be interesting things where if you want to trade off samples versus queries, you can do something interesting. We haven't really looked at that too much yet. Okay, so time is passing, and I should get on to the last topic of the talk, which is kind of a melange of a couple of different passive testing frameworks. So we're going to change the game now and make testing more challenging by taking away the tester's ability to actively query points that it's interested in. Okay, so no queries anymore. What's going to happen? Well, the way property testing algorithms work is they get to take a nap for a while they're just given a bunch of samples from some probability distribution, and then the algorithm gets to look at the samples, do some analysis, and say, I think it's, has the property or is far from the property. So arguably, this is closer, I think, to some kind of data analysis scenarios where you might not be able to make queries, right? Maybe if it's like the silly thing with the dinosaur bones, you can't be like, oh, I would now like a fragment of a femur or something. You don't get to make queries on the things you're interested in. You just get what you get from the distribution, okay? And another thing I kind of like about this general space of models is that it tends to veer a little bit more toward the flavor of like problems of testing probability distributions, which is this big, rich, amazing area where Clement has written multiple great surveys. And I think it's nice if we kind of have a little bit of a connection between function testing and distribution testing. So what I want to do in the next couple slides, next couple minutes, and then I'll close, just tell you about three, these are, not exhaustive at all, but three kind of representative ways that you can think about testing in a passive setting. So the first one is kind of just a sample-based version of the usual property testing model. So think of this as very much like standard property testing. You're testing monotonicity or juntas or something like that, but you don't get to make queries. You just get random labeled examples. So for monotonicity or juntas, you get random uniform x's along with their labels. That's the kind of access you have to the data. You can't say, oh, I want to query this point. I want to query this point. You just get what you get. Okay. So it probably is not too surprising. Testing becomes hard in this setting. Monotonicity testing becomes much harder. Junta testing becomes much harder. This is a challenging framework for testing. I want to point out convexity testing or state-of-the-art algorithms only use samples. And I don't think this is a good thing. I think it shows that we don't know how to use queries yet for convexity testing. I suspect there are better algorithms out there that exploit queries. Question, Leon? Or? Yes, I believe so. There's this recent work by Eric and I think Nathan Harms and Renata Ferreira Pinto on the VC dimension type stuff. There's this different notion of VC dimension for the distribution free testing setting. Yeah, I think quite a bit is known about it. Not by me off the top of my head at this moment, but things are known. Yeah. So anyway, this is one example of a framework. You're just making the usual property testing problem harder. Right? You just say you only get passive, random examples instead of queries, and life gets harder. Not too surprisingly. Maybe it's nice to have other examples of property testing frameworks where it's passive. Again, you only get random samples, but life doesn't just get harder, right? We have to change the problem somehow. So what I'll talk about next is something Shivam just talked about in the weekly seminar, but I'll keep it very brief. We're going to be interested in testing truncation using samples. So it's kind of a scenario which has a little bit of like a statistics flavor. There's some known background distribution, call it calligraphic D. What happens to the algorithm? Well, it's this passive testing framework. It just gets a bunch of random samples independently drawn from this distribution D. And what we're going to try to do is distinguish between kind of a null hypothesis and an alternate hypothesis. The null hypothesis is that, yeah, nothing happened. You just got samples drawn from D. So maybe if D is the uniform distribution and this is the cube, this would be the null hypothesis, that this is what the distribution is. The alternate hypothesis is that the samples came from D, but they were conditioned on some function which has a property you're interested in. Maybe the samples came from the uniform distribution conditioned on it being monotone, or came from the uniform distribution conditioned on it being a junta, or something like that, okay? So this is kind of a drawing of the two distributions in these two settings. What the algorithm gets is, of course, doesn't see the distributions, it just gets a cloud of data points. And maybe the cloud of data points came from the null hypothesis on the left. Maybe it came from the, that underlying distribution conditioned on some unknown function with this property you're interested in on the right. And your goal is to figure out which of these cases you're in. So it's like you're trying to figure out, was my distribution truncated or not? Where the truncation, the class of allowable truncations, is like the property now. So let's make this concrete. We'll play a little game. The background distribution will be this two-dimensional Gaussian distribution. The class of allowable truncations will be truncations by convex subsets of the plane. So this is a bona fide sample of, I think, 1,000 data points, which either are drawn from the standard two-dimensional Gaussian, or they're drawn from the Gaussian, I think I'm giving it away with my hand gestures, drawn from the Gaussian conditioned on some convex set. Which one does it look like? Yeah, it looks like it was drawn from a Gaussian conditioned on a convex set, which is what happened. But if you don't know the convex set, and it's a high-dimensional situation, this is not such an easy problem. You can't eyeball it and be like, oh, clearly it was from this case or that case. So there are a couple of recent results in this setting. We have very sharp bounds for testing truncation of a Gaussian by convex sets, an unknown convex set. Turns out that the sample complexity is just linear, exactly linear in the dimension. And some other class of functions we don't have to worry about, polynomial threshold functions. We also have sharp results for distinguishing whether there was truncation or no truncation by one of these so-called polynomial threshold functions as well. So this is a setting where it seems like you can kind of improve on testing and learning type results. But it's, I think, an interesting potential variant of some kind of standard property testing if you just get these samples. Okay, so the last technical thing I'll tell you about, 2 slides, is passive testing under a promise. So kind of looking at promise versions of property testing. Remember, when we think about normal property testing, we say that the unknown function is any function, like any Boolean function over the domain. We're going to be thinking now about giving you a promise, a potentially strong promise that the function has some property p, and we're going to be interested in figuring out whether it has some refined property p prime or not. So it's just a promise problem, right? The universe of all possibilities for the function, or all functions with the property p, and given that it has property p, we want to know if it has this kind of specialized property p prime or is far from having the specialized property. Okay? So in some sense, we're making life easier by giving you the promise that you have this property. By giving you the promise, we're making life harder because we only give you access to the passive problem, passive samples. So maybe it's best, given where we are on the clock, not to read this slide. The one-sentence version is you can study kind of a property testing variant of the so-called sparse recovery problem. What is sparse recovery? Well, you get these examples like x and then some linear function plus noise. Okay, in sparse recovery, if the linear function is sparse, you want to recover the linear function, and this has been studied to death. There are lots of algorithms known that work under different circumstances, and there's always some kind of dependence on the dimension, some kind of dependence on n to do the sparse recovery if you're actually recovering the vector. You can think about a testing version. Again, you only get these random samples, so it's passive, but it's testing. We don't want to learn, we don't want to do sparse recovery, we just want to figure out, hey, is the underlying linear function sparse or is it far from sparse? And here it turns out that there are Junta-flavored results where you get some sample complexity, which depends only on the sparsity parameter, like for Juntas, but with no dependence on the ambient dimension n. Okay, so I view this as like a proof of concept that there is potentially interesting life kind of in this passive testing under a promise kind of regime of problems. Okay. So I think I'm really out of time. This is the very last slide, or almost the last slide. Just to recap, we talked about convexity testing, my favorite problem, which I hope you'll all go off and solve. We saw these different frameworks, tolerant property testing or distance estimation, this recent framework of relative error testing. We saw a number of passive tested frameworks. So I think there's interesting stuff going on here. Hopefully you feel that way too. Just as a 30-second thing to encourage you to work on property testing of Boolean functions in case you're not working on it already. I think it's an area where there are a lot of kind of easy to state open questions. We stated quite a few such questions in this talk. It gives you an opportunity, an excuse to kind of branch out a little bit. It has connections to a bunch of other topics, Boolean functions, high-dimensional geometry, these kind of algorithmic statistics flavored problems. I also want to give a shout out to the research community. I've been here at Simons for 3 or 4 weeks now with the sublinear algorithms program, and they're a fun bunch of people, so you have the opportunity to have fun collaborators if you work in this area. And that's really it. I just want to close by saying thank you to all the collaborators who participated in the work that I talked about today. So that's it. Any other questions? We got all the questions during SUPUP.
So I mean, to level the playing field for the passive testing framework, could you consider either an object has a property or is stochastically corrupted from having a property, rather than adversarially not having a property? Is there some notion of I mean, or the
Yeah, like benign kind of distance. Right. It's funny you mention that because I remember wondering what something like that a while ago, thinking, oh, I don't know anything about this, but Clement will know about this. And I meant to talk to him about it and I never did. So yeah, that's a good question. So you're saying sort of not like a worst case epsilon ball kind of thing in terms of your distance, but you're not interested in like saying that like the property, you're still keeping the property as the property, right? But you're sort of only worried, you're okay with
doing with probability close to 1 that
For most one is stuck in the property and then corrupted.
Yeah.
As opposed to like starting outside.
Yeah. So you're staying kind of close to the property, and you want high probability to be catching things that are false. You may fail on some false things.
I see. So it's like you have a spectrum of maybe like as your distance to the property increases, your correctness, your probability of saying. That's a good question. I don't know of work like this. It's almost like a smooth thing instead of this like these hard shells. Yeah, that's an interesting question. I don't know of work like that. But if anybody knows of work like that, it's likely that that person is in this room or at Simon's right now.
So for the convexity testing, passive testing aspect you mentioned, is there like a natural version of tolerant testing?
Yeah, so for convexity testing, we have agnostic learning algorithms from just samples for convexity, and those easily give you passive tolerant testing algorithms for convexity. So yeah, this is the thing with convexity, right? We should be using queries. Instead, we're using like a samples only. It's based on a learning algorithm. It's even tolerant. So like there's really, I think, a lot of room for improvement there, but we don't quite know how to do it. Sorry to end on a down note with like something we don't know how to do. Too bad, yeah. Question?
So for your conjecture, like this equivalence between convexity testing and monotonicity, right? Like what would you like conjecture? Like is it some sort of an equivalence under some notion of reduction between properties? Like
yeah, I've thought about this kind of thing quite a bit. Like, oh, you know, something happens in the monotone world, what happens in the convex world, or vice versa. And I have not seen. So Leon kind of alluded earlier to. Sometimes if you're looking for results about like, say, linear threshold functions or polynomial threshold functions or something, you can be like, yeah, I'm going to simulate a Gaussian by adding up a bunch of bits and like a linear function over Gaussian variables. Well, if I replace each Gaussian by like a sum of a bunch of bits, it'll still be like linear. So in cases like that, there are reductions. In these less structured settings, I don't know of reductions. It just seems like you have the result in one setting and then the result turns out to be true in the other setting, but often the proofs use different machinery. And it isn't like you're inspired by the one setting to come up with the statement for the other setting, but like the proofs don't seem to translate very much. Yeah, that's a good question. Questions? Okay, well, thanks again.